Good morning, chemistry students. Here are your Chapter 8, Day 5 notes. So we're going to be covering part of Chapter 8, Section 3. We'll be starting at the start with 8.3 reactions in aqueous solution and finishing up with spectator ions. Again, a kind of reminder of where we've been so far. So in this chapter, you have learned how to balance chemical equations. And typically, again, you're going to be given a sentence, and you're going to take your sentence to a word equation. The purpose of that word equation is you're getting rid of extra information that's not important, and it allows you to focus on what is important. Once you have your word equation, you're going to take everything and turn it into symbols and make a skeleton equation. Remember, important for that is that your chemical formulas are written correctly. So you have to be asking if it's a compound, is this compound ionic or molecular? Remember, if it's an ionic compound, you're going to write the symbols, write the charges, crisscross, make sure it's the lowest whole number ratio. If it's a molecular compound, because it's made of two nonmetals, you're going to have your prefixes become subscripts. So you've learned how to write and balance chemical equations. You also have learned the 5 types of chemical reactions. There are combination or synthesis reactions, decomposition, single replacement, double replacement, and combustion reactions. And you have learned how to identify those reactions as to type so that you can predict the products. So remember that I've told you kind of throughout this that states of matter were not particularly important to me. But as we move forward and we start to talk about reactions in aqueous solution, with our goal being able to write a net ionic equation and predict whether a product's going to be dissolved in water or not, it does become important that you include your states of matter. So only when you're asked to do a net ionic equation or a complete ionic equation do you need to include your states of matter for me. That's going to be today, so we're going to make sure that as we work through this, we're always including our states of matter. So this section is about reactions in aqueous solution, and this is important because most ionic compounds, which are most double replacement reactions, take place with your ionic compound dissolved in water. So you're going to do a lab at some point in this unit, and you're going to do some of these reactions, and you're going to see that all of the solutions you use look the same. They're all clear liquids that have an ionic compound dissolved in water. So most of these reactions take place in what's called aqueous solution. So as we're going to kind of start to talk about working towards having a net ionic equation, realize that when we're talking about these reactions in aqueous solution, we are usually talking about double replacement reactions. And remember, you know that a reaction is a double replacement reaction because it has 2 reactants and they're both compounds. Okay, so these are usually going to be double replacement reactions, but they can be single replacement reactions as well. You may have one on a homework assignment at some point that is a single replacement reaction, but like in the lab we're going to do later in this unit, there won't be any single replacement reactions. Now, when we talked about double replacement reactions, one of the things we talked about was the fact that for us to know a double replacement reaction has taken place, one of 3 things has to happen. Okay, so double replacement reactions must produce a precipitate. Remember, a precipitate is a solid. So again, it's this idea that we have 2 clear liquids, and when we mix them, it suddenly becomes cloudy. So there's some sort of precipitate produced. Okay, so the precipitate is kind of the chemistry term for having a solid produced. Or, okay, we can produce a gas. And again, we're going to know a gas is produced because we're going to see bubbles. Or we can produce a molecular compound. Because again, remember, double replacement reactions, we're typically dealing with two ionic compounds. So if we produce a molecular compound, this is going to often be for us water. So most times the molecular compound that you're going to produce will be water. So again, these solutions, these reactions that are going to happen in these aqueous solutions, so these ionic compounds that are dissolved in water, okay, when we mix them, we usually have some sort of double replacement reaction, and something has to happen for us to know they've occurred. So we must produce a precipitate, which is a solid. We can produce a gas and see some bubbles, or a molecular compound and have water. This is important, and we're doing this because ionic compounds dissociate in water. So dissociate kind of means to break apart. Okay, so these ionic compounds, as soon as we dissolve them in water, as soon as we put sodium chloride, table salt in water, it's not sodium ions bonded to chlorine ions anymore. Okay, the ions break apart, so it returns to ions. Okay, so the ions break apart and they're floating around and moving around inside in that water. Okay, so ionic compounds, most ionic compounds dissociate in water, which means they break apart and return to their ions. So to work towards being able to write a net ionic equation, the first step we're going to do is to write what's called a complete ionic equation. The definition of a complete ionic equation is an equation that shows dissolved ionic compounds as free ions. So basically what we're saying here, or what I'm saying is, I'm going to take those ionic compounds that were compounds, and I'm going to break them up into their ions. So I'll have cations and I'll have anions. Remember, cations are positively charged ions, anions are negatively charged ions. Now, when we're doing complete ionic equations, again, we must include the state of matter. Okay, and just kind of as a review, these are written as subscripts, so they're small and down low. And so again, we have an S, and I usually use a cursive S so it doesn't look like a 5. An L, and again I use a cursive one so it doesn't look like a 1. Okay, so S for solid, L for liquid, a G for gas, and then dissolved in water is the AQ. Okay, for aqueous. So one time when I'm going to require you to include your states of matter is if the problem's asking for a complete ionic equation or a net ionic equation. Then states of matter must be included. So let's take a look at an example. And again, to get there, we're still going to go through all the steps we've been doing to write and balance chemical equations. So, of course, I'm mean, and I'm going to give you a sentence. Okay. So aqueous silver nitrate reacts with aqueous sodium chloride. So again, remember our kind of first step when we're trying to write and balance chemical equations is to identify the reaction as one of our 5 types. So we have a compound reacting with a compound. And the only type of reaction where we have 2 compounds reacting is a double replacement. So we know this is a double replacement reaction. Now remember, in a double replacement reaction, the ions kind of swap partners or switch places. So if we do our next step, which is we want to take our sentence and make it a word equation. So these are both reactants. So I have silver nitrate reacting with sodium chloride. Now, we said it was double replacement, and silver's a metal and sodium's a metal, so they're going to swap partners. So silver's partner is going to be chloride, and sodium's partner is going to be nitrate. And remember, these reactions always take place. So there's no like checking your activity series of metals. Remember, that's only for single replacement reactions. So now I have my word equation. Now I probably want to go ahead and kind of reference my states of matter. So if so I want to reference my states of matter, because again, that's going to be important because we're doing a net ionic equation and a complete ionic equation here. So it already told us that silver nitrate was aqueous, and I kind of like to add this up here. Now, eventually you're going to learn how to know this, but for right now, I'm just going to tell you that silver nitrate is aqueous and silver chloride is a solid. It's a precipitate. Okay, so now we have our sentence, right? We've written our word equation. Now we want to write our skeleton equation. So we have to make these all formulas. And silver nitrate is a metal and a polyatomic ion, so it's an ionic compound. And all of these are, right, because sodium is also a metal. So every single time I write the formulas for each one of these 4 compounds, I'm going to write my symbols, I'm going to write my charges, I'm going to crisscross the charges, and remember it's only the number, not the sign, and then I'm going to make sure I have the lowest whole number ratio. So silver is Ag, and it's on your helper sheet. And on your helper sheet, it only has one possible charge, so it's Ag with a +1. Nitrate that you have memorized is NO3 with a charge of -1, so nothing to do because I crisscross down once. Sodium is Na. It has a charge of +1 because it's in group 1A. Chloride is Cl. It has a charge of -1 because it's in group 7A. Again, I have nothing to do here because I'm crisscrossing down once. All right, silver is still Ag, and it's still on our helper sheet with a charge of +1. Chloride is still Cl. It still has a charge of -1 because it's in group 7A. And again, I have a +1, -1, so nothing to do. Sodium is Na. Still a charge of +1 because it's in group 1A. And nitrate is still NO3 with a charge of -1. Okay, so nothing to do. Now, I need to put my states of matter. So now I want to balance this. So as I start to look at this for balancing, 1 silver, 1 silver, 1 nitrate, 1 nitrate, 1 sodium, 1 sodium, 1 chlorine, 1 chlorine. This happens to be a skeleton equation that's also a balanced equation. So I don't have to do anything to balance this. This so far has been review. Hopefully you're pretty comfortable doing that. Now we want to do this complete ionic equation. We want to take this equation and we want to write it so that it shows our dissolved ionic compounds as free ions, as cations and anions. What that means, and maybe we want to kind of add that back here with some notes, okay, is what that means is everything that is the aqueous state of matter is broken down into its ions. So to write our complete ionic equation, we're going to take everything that has a state of matter of aqueous and write it as its ions, which means it's kind of nice that in our balancing our equation, we have our ions already shown. So what that means is silver is going to become Ag. Ions have to have a charge, and they have to have their state of matter. So we might want to add that, okay? So remember to write your ion charge and its state of matter. Okay, so Ag plus aqueous. Now we also need nitrate, so that's NO3, charge of -1, aqueous. Sodium chloride is going to break up because its state of matter is aqueous, so plus Na plus aqueous plus Cl minus aqueous yields. Now, silver chloride, its state of matter is solid, so it doesn't change. I'm going to leave it AgCl solid plus Na plus aqueous. Hopefully you have room to keep writing this on one line. I'm out of space. And NO3 -1 aqueous because sodium nitrate is an aqueous solution. So that, what we just wrote, this is our complete ionic equation. And again, it's a complete ionic equation because it shows everything that was in the aqueous state of matter as it's dissolved, as its separate ions. So again, because it's an ion, it has to have a charge and it has to have a state of matter. So we have silver ion reacting with nitrate ion, reacting with sodium ion, and reacting with chloride ion to produce silver chloride, and sodium ion and nitrate ion. So this is your complete ionic equation. All right, well, what do we do with this complete ionic equation? Because remember, the title of this section is we want a net ionic equation. So what's our next step? Our next step after we have our complete ionic equation is we're going to identify who the spectator ions are. Now, think about what a spectator is at a game, right? A spectator is somebody who is there and they're watching, but they're not actually playing in the game, right? They might be cheering people on and they might be kind of helping out, but they really are not participating in the game. These spectator ions are pretty much doing exactly the same thing. They're around, they're dissolved in that water, but they're really not participating in the chemical reaction. So the definition of spectator ions are ions not directly involved in a reaction. Now, how are we going to know that they are a spectator ion? Spectator ions are the ions that appear in the exact same form and by exact same form we mean they have the same symbol, they have the same charge, they have the same state of matter. All three of those things have to be exactly the same. Okay? So they exist in the exact same form on both sides of the equation. And again, these spectator ions are not really participating in the reaction. And because they're not really participating, we can leave them out. Okay? Again, this reaction can happen whether those spectators are there or not. Okay? So, we want to identify who the spectator ions were back in this reaction. So I'm going to try to rewrite this reaction here. I can make it work. Ag plus aqueous plus nitrate aqueous plus sodium ion aqueous plus chloride ion aqueous produced that silver chloride, which we didn't break apart because it was in the solid state of matter, and the sodium ion aqueous and the nitrate ion aqueous. So now we're looking for our spectator ions. Which ions appear on both sides of my arrow in exactly the same way? Well, if I look at my silver does it because it's part of the compound. Nitrate does. Okay, and sodium does. Does chloride? No. So to identify my spectator ions, I have two choices. Okay. Choice number one, I can write their formulas. So I can say it's NO3 -1 aqueous and Na plus aqueous. That's one way that you can identify them. Or you can use their names. So you can say it's nitrate ion and sodium ion. It does not matter to me which way you choose to identify them. But if I ask, or if a question asks you to identify the spectator ions, you have to specifically identify them somehow. So that's where we're going to stop for today. We're going to pick up talking and continuing to talk about these spectator ions as we continue. Have a great day, and I'll talk to you tomorrow.